Okay, so we've seen our center of mass for lamina, we've seen for 2 dimensions, we've seen the center of mass for 3-dimensional objects. But what is center of mass doing for us, right? We want to tie this to the entire study of motion. So this is all the object alone. Yes, we did use moments, but what does the center of mass do? And that's what we want to investigate. So now we will try and investigate the center of mass of a 3-dimensional body, whether it's uniform, composite body, non-uniform. We won't worry about that. For the sake of this, let's believe we have a center of mass. What is it? What does it do, right? So when we talked about the lamina discussion in one of the last core concepts videos, I talked about there being a center of mass and a point at which the framework or the lamina being hinged, etc. And I want to extend that here, right? So let me, obviously for a 2-dimensional plane, I had my little very flat plastic ruler that I demonstrated. Extend that concept again and take a solid object and say, where does that solid object come to rest? And perhaps a clear illustration would be if I went back to my, let me take something like this. So I have a solid object here. This is fairly solid, but it almost always, if I let it go, it's just going to be in such a way where it subtends a nice, the shape is even around. You always intuitively say that this is hanging in such a way where its center of mass, obviously for a circle, the center of mass is at its center, and that center is right below the point at where I hinge it. So this is sort of the logic that I want to state to you, and it's very straightforward. We don't have to do a lot of math about it, but the math that you need to remember for the exam is something like this. So we'll start with a cylinder, right? So I have my cylinder here, just because I want a simple shape. So I have my cylinder there, right? 3-dimensional cylinder. I have its axes here, right? And I know very well if it's uniform, or non-uniform, you can work it out. You can define its center of mass to be somewhere here, right? So I will use another color and say, okay, that's my center of mass. Now, what happens if in reality, the center of mass is where I am expecting to see the mg pass through, right? This is where mg is passing through. If I suspend this cylinder on 2 sides, so for the suspension, I will use a string here, and I will use a string here, and suspend it neatly on top. It's a nice, neat suspension. What I should expect to see is inelastic string equal length, right? Inelastic string equal length. So this plane here and this is 90 degrees. So if this is the radius, that's 90 degrees. All nice, neat. I should see some kind of a tension T here and a tension T here. And I can fairly easily and intuitively say 2T is equal to mg. Everything looks nice and easy, right? It's simpler to understand. However, this thing can now take a few different forms. Now what if, and obviously I could flip this around and hang it like this equally, nothing would change. 2 strings and center of mass, it'd be the same. So it will look like that. Center of mass here, my strings are here. All good. I don't have a problem with it. But where it begins to get interesting is if I now say, instead of this setup, I have a setup where I want to, and let me just do it this way. Again, if only I could get my artistic skills honed up. Now I have tilted it by some angle and I'm still counting on a string here and a string here, hold it. What do you think would have happened to this setup? And if I tell you it's an equilibrium, then we have a really interesting problem, because we know that if it's uniform, it's somewhere in the center here. I have my little center of mass here, which means my G is acting, my mg is acting here. You can do the math now and say what has to be the tension on these. You could not have, would you be able to have equal tension? This is the problem that we get to when we start evaluating this part, right? Just to understand how bodies pivot. So normally, if it was just a single pivot, or if it was just hung here, it would be quite safe to say that my cylinder has a center of mass here, is hung up here. It will be fairly straightforward to say that this is one single straight line along which both mg and T pass and cancel them each other out. Just like how we had in a lamina, in a three-dimensional object with the exact same thing, center mass, you would get a perfect line. A simple problem in an examination could just be to ask you what say this angle theta would be. That could be a very simple problem in an exam, right? But a complex problem, more than 5 marks, maybe even more than 4 marks, could be a problem set up like this, and to ask you to determine the tension in these strings as a function of mg. So if I have T1 and T2, what is going on in holding this in equilibrium? And the simple answer, if you haven't guessed it yet, is to take moments about this. You could write this. Two equations get formed here. I'm going to change my colors. Got regular white color. Two equations get formed here. One is T1 plus T2 is equal to mg. That's the resolution of all forces in the vertical direction. That's one. And the other is by taking moments about, let's say, points A and B, and taking moments about A and B. And if I take moments about B, I'd have to ascertain this perpendicular distance and this perpendicular distance, right? And then do the equation for the moment, which is mg times whatever this function is. Let's say it's a small b and this is a small a, times small b is equal to T1 times the small a. And then if I could take a moment about this one, I would do the same, applying these and try and solve them. So that's typically how you would go about approaching these problems. So they can make it reasonably complicated for you, but usually not too bad. Usually not too bad. But the part where it gets really attractive is when they give you a composite object or a body that is non-uniform, and then position these tensions in at certain locations. So yeah, you find out the center of mass, then you do the equation, and then finally the question is basically asking you to determine, say, it asks you to determine this angle, theta. So there's a geometry that's come in. Usually with a problem like this, they won't push you to doing integration to find center of mass. It will be something more simpler using formula, and then the force equations, mapping the force equations, getting the moment right. Those would be the challenges. But that's typically the first part of what I wanted to address in how center of mass gets applied. And that's one of the build-up of learning center of mass, getting that center of mass into two-dimensional objects, using calculus, and then building it to three-dimensional objects, all to understand how the forces get balanced out and what an equilibrium position means. The equilibrium position, if it's a single hinge, means that your center of mass is in line with the point, and the tension and reactive forces all pass through the same axes which contain the center of mass and the point of pivot or hinge, or point of suspension as they call it. If it's equilibrium with multiple points, then you go with the moment of all, the net vertical direction or net vertical and horizontal direction of all forces is zero, and the moment about any point is also balanced. That's the approach. You know these two, I think you're pretty set, right? The bigger challenge will be to come up with the values of the actual center of mass itself. That's where the integration is. Okay, so that, I think that addresses the first part I wanted to talk about when it comes to center of mass application. And now for the second part, which is my favorite part, because I often used to draw this, and what I normally used to draw is my favorite inclined plane. So now I get a chance to draw my inclined plane again. That's my inclined plane, and I always love to draw my body on it, which used to be the little box that I used to have. So that was my box that I always put on the inclined plane. Also something I really love, and I used to put a little dot here and draw my arrows here. But now this is let's say it's a square box, three-dimensional box with square sides, square faces. I bang in the center, have a center of mass. I want to now discuss a couple things, right? And now let me also I won't draw the horizontal, but I'll just, for the purpose of your understanding, I will draw a theta. Okay, now that's what I write. I really love, this is where it all comes together. This is where it all comes together. What's going on here? If this object is stationary, there is friction, of course, sorry. Don't forget that. So we've brought everything together here. There is friction, coefficient of friction is mu, right? Mass is m. Acceleration due to gravity is g, things that we know. Wait, I can also define normal reactive force here, right? That's the reaction force, that's normal reaction, R normal. I can also define friction. F friction is equal to mu R normal. I love that. Okay, what are we doing? Let's take a look at this, and let's understand why center of mass becomes so important for us. I should probably draw my my box a little bigger, just so it's doesn't get all crowded up here. So let me make that bigger, and my box now can be, it's a big box. Yeah, there we go. Lovely. Love that. And there you go. My center of mass is there. Love the big box. Beautiful, beautiful. Now, that is clear. The combined mass feels like a mass at that point, which then creates the force down here. Now that we understand mass, center of mass, we will also know that there is that little, so it is not at the center of the object. It is instead at the point where it feels this. So your reactionary force, and in this case for the reactionary force, I am not gonna worry about the vertical component, but I will draw the normal component and say that is where my normal reaction applies. So you can now see what is going on this object. Previously, we used a simple case. We just put the box there, and then we said, oh, that's where the R is, and that's where the mg is. No. It's very different now. Now we know how to treat this object. Now we know. And that is why knowing the center of mass is important, because there are a few implications. If this is on a plane theta, where it is about to, so now what's happening is you do have mg, which means there is a force almost acting as if it's pulling me down here, right? Which we know very well from all our previous work is mg sine theta. It's pulling me down. However, friction acts there in the opposite direction. Frictional force F friction equal to mu R n is acting there. Now all of a sudden, not all forces are brought here. The forces are where they're acting. The frictional force appears like it's acting right there because it's effectively all over the place, but it's normal, so it's like pulling the box from there. Now you appreciate what is going on. You can clearly say that right at that point of equilibrium where I am defying the frictional force, yes, this is the maximum frictional force, Ff is equal to mg sine theta. On that direction, they cancel out. We are good. It's not going to move. It's right at that tipping point. That is fine. However, there is another piece that we have to worry about. As I approach this theta, if I raise my theta up, I could say, hey, you know what? If you raise theta up even more, as theta is beginning to go towards your 90-degree mark, your mg sine theta is becoming higher, more force, you're going to beat friction, you're going to move down. What's going to happen? You are sliding that process. So here's the key. So when my mg sine theta, okay, begins to become greater than frictional force F, and imagine at limiting theta, it's equal to mu n, mu Rn. Rn could be written as, Rn, I should have written that too. So Rn itself could be written as mg cosine theta. If my angle is higher, cosine theta suddenly is becoming lesser as I approach 90 degrees. Mg cosine theta is dropping, Rn is dropping, Rn times mu, frictional force is getting reduced, which means I can now exceed frictional force and I would slide. The result would be, I need another color. What color? Well, along this direction, I would slide, S-L-I-D-E, slide. This is the concept of sliding. You would slide. But, what if that is not the case? What if I have an extremely high friction? Very rough. So I approach a value of theta where I've raised it up significantly, but mu is very high, so even though Rn is dropping, now I'm raising theta, but I get to a point where as theta changes, something else is changing. It's not just the force, but as theta changes, if you have not guessed it, as theta changes, this point, so remember, this is a box, right? And this is the box, and assume it's a square box, right? Assume it's a square box of side A, and side A, and assume it's a square box. Sorry if it looks like a rectangle, right? But something is changing, and what is changing is this. As theta increases, this segment here, x, is changing. As I increase theta, g keeps appearing like it's coming over, mg is moving this way. There comes a time where this picture will look something like there will be that time where you see this. There will be some angle alpha at which, if your friction is solid, really high friction, right? This one is the same. So this is mg cosine alpha, r with subscript of n, is still mg cosine alpha. This is cosine alpha. This is sine of alpha. However, x has gotten really small. Now what happens? Yes, you've got solid amount of friction. It's very rough. mg sine alpha is only equal to the frictional force. Remember, until we beat friction, we're always equal to. We're never less than, because friction automatically adjusts itself downwards, right? We're less than equal to the frictional force. So there is no sliding, which is equal to saying we're equal to or less than. So it's actually less than equal to, right? Mu times mg cosine alpha. Okay, mg cosine alpha, you make the adjustments, you will see here tan mu is always greater than equal to tangent of alpha. So whenever the coefficient of friction is greater than the tangent of alpha, then you are not going to slide at that angle of alpha. But at that angle of alpha, if the geometry of the object, right, the three-dimensional geometry of the object is such that the center of mass has caused this x to be 0, which is effectively saying my center of mass is now not on top of my base. Then what happens? Then suddenly the most wonderful things begin to happen, because what you would do is you always take a moment about this place. If you took a moment about this now, you have this force here and you have this force here, you would notice that it's quite secure. These forces are much larger, mg is much larger. The effect of the mg cosine theta and sine theta effectively cancel out with mg, and you're fine. It's not going to move, right? And obviously, if you came all the way down, mg sine theta became 0, and this becomes equal to mg. So you have two equilibrium forces. So pretty much they stay the same until they get to this point where the effect of mg just kind of disappears, because then you really don't have mg doing anything. The only force that can create about this point a meaningful moment is mg sine alpha. And the moment you do that, what you do is you've created an object like this with a moment here and a force acting normally. The object will turn. So this object will turn, and the action at that time will be called toppling. Topple, topple. topple. So yes, I can define an alpha where, as long as tangent of alpha remains less than mu, there won't be any sliding because mg sine theta. But also, I can define an alpha, so there might be two different alphas. I can define an alpha where the center of mass is outside of or just begins to get outside. So like a limiting alpha where it's just there. Well, in many cases, even if it's not just there, even if it's inside it, there are cases where the object is so heavy or there's very little friction, there's very, the normal reaction is very low, you would still have mg sine theta at a reasonably high theta, it could create the object to fall. So even if you were really heavy on your legs and light on your body, there's still that one final angle at which it doesn't matter, you would fall. And of course, it was the other way around. You were very light on your legs and you had a big heavy weight that you were carrying there. All it needed is a slight tilt and you would fall down, which is why when you carry a heavier object, you tend to go off balance more because your center of mass is so high, it's really outside the area that your feet create. The geometric projection of your three-dimensional footprint onto your two-dimensional base. Your center of mass moves out. So that's the idea here. So this is very important. Keep that in mind. Sliding and toppling, and the positioning of the question could be giving you another force here. And that's where they introduce a variable. They say, hey, if bang in the center of this, I've got another force, then what is the value of that force that will prevent toppling but allow sliding? So to prevent toppling, moment has to be balanced, right? But allowing sliding means mg sine theta minus this force should be greater than frictional force. If you want to apply a force here but still slide down, mg sine theta minus the applied force should be greater than the frictional force. And it will still slide. And to prevent toppling, the moment about this point should cancel out. So understand these. Know where Rn applies. Usually the problems will kind of indicate to you that normal reactive force applies 2 centimeters away from point A or something like that. Understand, they're going to give you the idea of where the tilt is. But this is where it all comes home. You've got your friction, you've got your center of mass, the geometry. Imagine a problem in the exam. They give you a cylinder and a hemisphere, 2 different densities, tell you that it's combined, put it on an inclined plane and tilt its angle and then ask you to find a theta at which it would topple or a theta at which it would start sliding, or a coefficient of friction which would prevent it from sliding but allow toppling. You can have a lot of permutations on this, but if you understand this mechanics, remember when you do sliding, you're doing a net effect of forces. When you're doing toppling, you're doing moment, right? So that is it. So that should complete the whole center of mass. Further center of mass, as they call it, pretty much an A-level piece only. Didn't see it anywhere before, but this is very, very interesting, and it's actually the homecoming of the concepts that one needs to get into some hardcore mechanical engineering. But yeah, I'll leave you with this, some interesting problems to do. But if you know how to do your center of mass, and if you've already done core concepts and know your forces, this should be a breeze. I'll see you in the next video where we talk about kinematics and the varying acceleration problems. But this is it. Good luck.